Good morning to everyone. This is Dr. C.H. Nagaraju, Annamacharya University. Today, we are going to discuss about the DC biasing concepts of bipolar junction transistor. Everybody, we know that the biasing concept is very, very important for the amplification of bipolar junction transistor. See here, I would like to how to apply the biasing concepts and what are the various types of biasing concepts in amplification. See, first of all, I would like to see that what is meant by the biasing. The biasing is nothing but applying an external voltage to the circuit to make the device into active state. See, it is nothing but the biasing. See here, the DC voltage is applied to a transistor in order to turn it on and so that it can amplify the AC signal. See, what is operating point? See here, if we see that a graphical representation of output characteristics of the CE configuration, see here the output characteristic is plotted in between the VCE versus IC. The VCE can taken as on x-axis, IC has taken on y-axis. See, if we plot the output characteristics in between IC and VCE, see by keeping various values of base current. See, base current is equal to 80 microampere, 70, like that. See how the base current is kept constant from IB is equal to 0 to IB is equal to 80 microampere. See, by seeing this one, see how the output characteristic is observed from this graphical representation. Next, we move on to the topic of discussion. See, in case of the output characteristic of CE configuration, see, we have observed mainly three regions. One is the cutoff region, and another one is active region, and third one is saturation region. See how these three regions are determined. See, in case of active region, see, we are well aware about that. See, the base emitter junction is forward bias, that is input junction is forward bias and the output junction is reverse bias. Coming to cutoff region, see, base emitter junction is reverse bias. See, cutoff region is the region where the amount of base current is below the zero level. And come to saturation region, see, in saturation region, both input junction and output junctions are forward bias, which means that base emitter junction is forward and base collector junction is also forward bias. See, by doing like that, just we can operate the transistor in different mode of operations. Either it may be active mode, or it may be cutoff mode, or it may be saturation mode. See, no matter what type of configuration of a transistor is used in the circuit, but the basic relationship between the current components are always the same, and the base to emitter voltage is a threshold value. See, this threshold value, simply we say that it is a VBE value. See, VBE is nothing but it is the voltage in between base and emitter. See, approximately it is 0.7 volts for silicon and 0.2 to 3 volts for germanium. See, if we see here, this VBE voltage is equal to 0.7 volts. And I is the emitter current. It is almost approximately equal to output current, which is nothing but collector current IC. See, this IC is equal to 1 plus beta times of IB. Already the basic expression, everybody, we know that IC is equal to beta times of IB. See, the operating point, how we define the operating point? The operating point defines where the transistor will operate on its characteristics curves under DC conditions. Say, for example, for linear amplification, certainly we have to maintain the minimum distortion. See, for that, the DC operating point should not be too close to the maximum power and also voltage, or it may be current. See, here we should avoid the regions of the saturation and cutoff region. See, in case of amplification, the most probably the transistor is operated in active region. Next, coming to have a small look on the different types of the biasing concepts in BJT. The very fundamental method is a fixed bias method. Second one is emitter voltage or emitter stabilized bias circuit. Third one is voltage divider bias. And the last one is DC bias with voltage feedback. See, these are the different types of biasing concepts we are going to talk about, talk in case of amplification. See, coming to have a discussion about the fixed bias. See, in case of fixed bias configuration, the base resistor is directly connected to the DC biasing voltage. But it is not so much of stable. And second point is most important thing is, see, most configurations, the DC analysis begins with the determination of the base current. And for the DC analysis, the transistor network and also all the capacitors are replaced by open circuit. See, obviously, for DC analysis or for DC equivalent circuit, see, all the capacitors are acts as a open circuit. Then we move on to the draw a DC equivalent circuit of a fixed bias. See, if you see the figure of a fixed bias circuit, see here the capacitors C1 and C2 are connected at the input and output side, and the base resistor is directly connected to the DC biasing voltage VCC. See, that's why it is a fixed bias circuit. See, for DC analysis, these capacitors C1 and C2 are acts as a open circuit. See, then see we are going to see the equivalent circuit of the fixed bias. See this figure. This is the DC equivalent circuit of fixed bias. The power supply VCC is applied both on input side and also output side. And here we are going to identify the current components on input and output side. IB is the input current and IC is the output current. And voltage in between base and emitter is VBE. The voltage in between collector and emitter is VCE. Then I would like to apply the Kirchhoff voltage law for the input loop. Yes, next. See here, by applying the Kirchhoff voltage law at the input side, VCC minus IBRB minus VBE is equal to 0. This is the voltage, Kirchhoff voltage law is applied in a input side. Already we know that what is KVL. The algebraic sum of all the voltages in a closed loop is equal to 0. So based on the concept, just we are going to apply the KVL equation at the input side. See, from that expression, see, we are going to determine the base current IB is equal to VCC minus VBE by RB. Similarly, we are going to see the output side and apply the Kirchhoff voltage law on the output side also. See, the output current is IC and the output voltage in between collector and emitter is VCE. Now we are moving into apply the KVL. See, what is the KVL? See, KVL is nothing but VCC minus ICRC minus VCE is equal to 0. Or VCE plus ICRC minus VCC is equal to 0. See, from this expression, determine the collector current IC. IC is equal to VCC minus VCE by RC. See, after determining the input current and output current, then we move on to the determine the operating point on a DC load line. See, before we are going to determine the operating point, let me see a small example under the fixed bias configuration. How we determine the IB, IC, VCQ, and VB, VC, and VBC voltages. See, if this is the figure, the DC bias voltage is 12 volts and beta value is 75. Resistor RC value is 2.2K and RB value is 240 kilo ohms. Obviously, the capacitors C1 and C2 are replaced by open circuit. Then determine IB. Already in the previous expression, see what is the formula for IB? IB is equal to VCC minus VBE by RB. See, by substitution in this expression, VCC minus VBE by RB, simply we are calculating the value of IB. And similarly, we are going to calculate the IC value. IC is equal to VCC minus VC by RC. See, here we have to determine IC value also. See, once we know the IB and IC, it is very simple to determine ICQ and IBQ. See, once we know the values of ICQ and IBQ, so simply we are going to determine the Q point on a DC load line. Next, coming to a small discussion on various regions. Already cutoff region, we know that. Coming to saturation region. In saturation region, both input and output junctions are forward bias. Therefore, the transistor is operated in a switch in a saturation region, just like it is a forward switch. And here, the current is maximum. So this is a small figure represents the saturation point, how the saturation point is identified. And these are the simple calculations already just we can observe in earlier case by applying the KVL for input side and also output side. This is the saturation current. IC sat is nothing but it is a collector current saturation value, the VCC by RC. And see here by applying the given values here, the saturation current is 5.45 milliamps. This is the maximum current amplified in the transistor. And this is the load line analysis for fixed bias configuration. And we can clearly observe that how the signal is amplified here. By keeping various values of base currents from IB is equal to 0 to IB is equal to 50 microamperes. This is already, we know that. See how to establish the operating point on a DC load line. On x-axis, just we have to take the scale of ECE. On y-axis, we have to take the scale of IC in milliamperes. And after that, determine the operating point both at x and y axis by applying boundary conditions or the extreme points for generalized transistor equation. See, the extreme boundary point on y axis is VCC by RC, and the extreme boundary points on x axis is VCE is equal to VCC. See, once we know these 2 points of VCC by RC and VCE is equal to VCC, draw a line by passing these 2 points. And this is nothing but a DC load line. And after determining the DC load line, the output characteristic of CE configuration is embedded onto the DC load line. Then we are identify or determine the Q point on a DC load line. See, from this figure, what we understood is how this Q point is switching from on a DC load line for various values of IB1, IB2, IB3. See, simply it is nothing but once the Q point movement is happened in case of amplification, certainly we know that we are not obtaining a faithful amplification. See, in order to avoid that one, we are always maintain a constant output current. So once we obtain a constant output current, the Q point is stable. See, then only we are obtaining a faithful amplification signal at the output side. This is also how the effect of increasing the level of RC on Q point. Even the value of RC changes, the Q point is also changes. Next, we are going to talk about the emitter stabilized bias circuit. See, why particularly just we say that it is a stabilized bias? See, already, see, we have the drawbacks in fixed bias. In case of major drawback in fixed bias, the stability factor S is equal to 1 plus beta. If beta value increases, stability factor value is also increases. See, that's why the fixed bias provides the food stabilization. See, therefore, we are moving into the another designing concept. It is nothing but emitter stabilized bias circuit. See, here we are adding the one more component, which is nothing but a resistor component is added at the emitter terminal for providing better stabilization. See, this is a circuit diagram of emitter biased circuit. See, particularly, we are going to draw a equivalent circuit for input side. See, that's why apply the Kirchhoff voltage law for the input loop, which is nothing but VCC minus IBRB minus VBE minus IERE is equal to 0. Similarly, we are going to apply the Kirchhoff voltage law for the output loop. VCC minus ICRC minus VCE minus IERE is equal to 0. See, from this expression, see, we have to calculate the IC value from the output loop. And from the input loop, we are going to calculate the input current IB value. See, almost we know that IC is approximately equal to IE. See, this is a small example for the emitter bias circuit. Next, coming to how the stabilization is improved in case of emitter bias circuit compared to fixed bias. See, this tabular column can give the clear information how the stabilization has to be improved in case of emitter bias. Next, coming to the saturation level in case of emitter bias. See here, previously IC sat is equal to VCC by RC only, whereas here IC sat is equal to, that is maximum saturation current is equal to VCC by RC plus RE component. See, this is already we discussed in the earlier case how load line analysis can be determined for both DC and AC analysis. And this is most important concept in case of biasing circuits. The voltage divider bias circuit is very, very important and most commonly used biasing concept. This is voltage divider bias. See here, both we are applying a potential divider circuit at the input side. See, with the support of DC power supply VCC, resistor R1 and resistor R2. So this potential divider circuit provides more stability for the amplification. And here we can see that the exact analysis and approximate analysis. See, this is the circuit was developed for exact analysis. See, here we are moving into calculate the input voltage and input current. For the calculation of input voltage and input current, the complicated circuit is simplified into a simplified circuit by applying the Thevenin's theorem. See, already we know about the Thevenin's theorem. See, we are going to identify the Thevenin's equivalent circuit. The Thevenin's equivalent circuit is V Thevenin's in series with R Thevenin's. That's why first of all calculate the V Thevenin's and also R Thevenin's. What is V Thevenin's? V Thevenin's is equal to power supply voltage or DC biasing voltage VCC into R2 by R1 plus R2. Similarly, R Thevenin's is equal to R1 parallel to R2. See, after that, we are going to draw an equivalent circuit with V Thevenin's and I Thevenin's. Then apply the KVL for the input loop. And apply the KVL for input loop is nothing but E Thevenin's minus IB R Thevenin's minus VBE minus IERE is equal to 0. See, from this expression, see, we are going to calculate the input current IB. IB is equal to E Thevenin's minus VBE by R Thevenin's plus 1 plus beta times of RE. And then apply the KVL for the output loop for determining the VCE. VC is equal to VCC minus IC into RC plus RP. This is the another method of calculation is nothing but approximated analysis method. See, these are the calculations given for the approximate analysis method. And here also we are calculating the maximum current at output side and determine the cutoff regions and saturation regions for the respective voltages and currents. And another one is DC bias with the voltage feedback. See, it is also nothing but connected to base biasing circuit. This is the another name has given to this one, connected to base bias, which means that it is a feedback provided from output to input through resistor RB. And here also apply the Kirchhoff voltage law at the input side. See, VCC minus ICRC minus IBRB minus VBE minus IARE is equal to 0. Then see, we have to calculate the IB value. IB is equal to VCC minus VBE by RB plus beta times of RC plus RA. See, this is the input current obtained by applying the Kirchhoff voltage law at the input side. In similar way, we are going to apply the Kirchhoff voltage law for the output side and identify the KVL expression for the output side. VCC minus ICRC minus VCE minus IERE is equal to 0. See, from this expression, see, we are going to calculate VCE value. VCE is equal to VCC minus IC into RC plus RE. See, after determining these values, see, we can see that the current components and the voltage components for various regions, cutoff and saturation regions. And then we move on to the bias stabilization. The stability of your system is measure of the sensitivity of your network to various variations in the parameters like beta, VBE, and also IC0. And these are the figure representations how the stability factor is provided for various Q values, Q point values.